Previously, we had talked about how to prove the correctness of a DFA. Namely, we talked about this idea of having an invariant. We've seen an example where we didn't necessarily need the state invariants that we came up with. So recall, a state invariant is where we try to see what's going on at each one of the states. So I want to know what property does it have if a string, upon reading a symbol, transitions into some state, and we do it for all of the states. Now, in our example, I did it with all the states, even though our DFA had a much more specialized structure that didn't require such a thing. As discussed there, you could specialize the argument much further. But I want to show you how you can use the idea of proving the correctness of a DFA using state invariants. So let's consider another example where it might be a bit more helpful. So let's consider another example. Now, I'm going to revisit a DFA we designed previously that was meant for recognizing all binary strings that contain a substring that is a 0 followed by a 1. So recall, we designed a DFA, and I'll give it a name. I'll call it M sub, that claims to recognize all binary strings that contain the substring 0, 1. So for those that aren't acquainted with terminology, substring is just simply a string that's within another string. So this is the design we came up with. We tried to come up with a role by designing a pathway that says the sequence of symbols 0, 1, because we need to have that appear somewhere in the string. But whenever that doesn't appear, I want to make sure that I can still read more of the input. So in this case, what I was able to do was, just because the pattern is 0, 1 like this, I can keep reading more zeros until I get to the 1, and regardless, I would get a 0, 1. So we took advantage of that property when we designed the DFA. So upon getting here, it didn't matter what else we read. A 0 or 1 would have been fine. Let's name the states Q0, Q1, and Q2, where Q2 was the final or accepting state. So notice that to get to Q2, you have to eventually read a 0, then a 1. And we have this one specifically in here so that we can keep reading zeros if need be until we hit a 1. And in either case, it would be that it's 0, 1. So please keep that in mind when we're thinking about state invariants. So this was our DFA. I'm going to call it M sub. We're going to prove the correctness of this DFA. So what's the first thing I suggested we do in our argument? Is try to identify state invariants to make it easier for us to see how we can establish, via the definition of an extended transition function, how we can prove that this DFA does exactly what we designed it to do, okay? But the thing is, we need to make sure, because we can't just say something then it magically becomes true. It's that way there has to be a reason why it's true, right? It could be just incidental that something we said was true, but it could be the case that it's wrong, like dead wrong. And in this domain, you don't want to be wrong, okay? So let us identify state invariants. So reminder, state invariants, this property is going to always hold during the processing of the string. So we're going to identify state invariants, one for each of the states. So for any one of the binary strings, we're going to identify some state invariants. So the first thing is, let's look at Q0. So what does Q0 have in relation to this? So do you notice that if you think about it from the perspective of us trying to detect 0, 1 as a substring, Do you notice that we never read any zeros yet? We can read as many ones as we'd like in Q0, right? You can read as many ones, but there's no zeros that have been read. So this might be a good way of proposing a state invariant. So delta hat Q0, so upon starting in Q0 and I read W, it's in Q0 if and only if W contains no zeros. No zeros. So I'm going to call this language I'll call it LQ0, just to be consistent with my, my notation. So this seems like a pretty reasonable one. You would agree that this makes sense, right? Like we haven't read it, and there's no way you can get back into Q0, right? So let's think about Q1 now. Actually, before we get to Q1, let's go about Q2. Q2 is the easy one, right? Because as soon as you get to Q2, what we need to prove, because remember, Q2 is the final and accepting state. If we did indeed do this correctly, it has to be that it only accepts when it contains the substring 0, 1, right? When the input string W does, right? So that should be the invariant for Q2. It's the only final or accepting state. So when Q0W is equal to Q2, if and only if W contains substring 0, 1. So I'm going to refer to this as LQ2, just to make this easier for us to see. And then, of course, this middle one. And you remember I talked about how this middle state, the Q1, isn't just simply, oh, I read a 0, right? It isn't just that. There's something really neat that's going on with Q1. So it has at least one 0, right? That we know for a fact. And it didn't read this substring, right? It hasn't yet. But it may have a bunch of ones that have been processed first, and then it read a 0, so there's at least one 0, but it hasn't yet read 0, 1. But there's another thing that's going to be really helpful if we want to think about how we might approach the proof of correctness using an induction proof. So think about it. So at some point, there's going to be cases where I'm in Q1, and then I transition to Q2, and in that case, it detects substring 0, 1, right? Well, if you think about that, what would you like this string to end with? What does it actually end with at every point? So this is where you have to think very carefully about this. So what a string will look like over there, it may have a bunch of ones. It may have no ones, for example, but it may have zeros, right? But what's the point? Regardless, it always ends with a 0. Do you see that? That's a very important and astute observation that will make this proof much easier to accomplish. So that I want to bake into our invariant. So it's not just that there's at least one 0. In fact, it always ends with a 0 if it's in Q1. So upon processing string W, if we're in Q1, if and only if W ends with a 0, but does not contain substring 0, 1. So I'm referring to this as LQ1. So notice I've defined a language for each one of our invariants. And now something that's really important to notice about this. Notice that this contains no zeros, right? This one contains at least one 0, but it doesn't contain the substring, right? But this one contains the substring, but it includes everything else, right? So that note that also includes the cases when it ends with a 1, right? Likewise, this can also include cases when it ends with a 1, as long as it has no zeros in it, right? this one contains at least one zero, that contains at least one zero. In fact, let's go through them all pairwise. So notice that, so this one contains ones with no zeros. It can have as many ones as it wants. This one ends with 0, but it can have ones before it. And it could have more zeros, but it doesn't contain this substring. This one contains everything else. So, why? Because notice this time it actually contains the substring, but it has no restriction on the fact that W ends with a 0, right? It can end with a 0 or a 1, and it has the substring. And it has to have at least one 0, right? So it's not in here either. So please note that LQ1, if I take the union of all three of these languages, this is the set of all binary strings. So every one of the strings will fit into one of them. And all three are disjoint. They don't overlap at all. I left some reasoning, which I just verbally stated in the notes. So if you were looking to go through this, I encourage you to think about why this is the case. So notice that, like I said, the invariant that we really care about for this is this one, right? That's the one that we use for the correctness. However, it's possible to get into Q2 from Q1. So it's going to matter a lot that we carefully crafted this invariant as we did here, for example, to account for the potential possibility we're going to have to append a 1 after, but I need to make sure there's a 0 just before that. That's why I designed the DFA like this, is that I want to make sure the pattern 0, 1 appears, even if I put more zeros in. Because I'm following the steps. So that was step 2. Now we're going to step 3. Given DFA M sub and any W that is a binary string, it has to be the following. So we're going to go through each one and describe the state invariance for each one. So we got Q0, delta hat Q0 W is equal to Q0, meaning that after the DFA M sub processes string W, it has to be in Q0 if and only if W contains no zeros. Q1 delta hat Q0W is equal to Q1 if and only if W ends with a 0 and does not contain substring 0, 1, and then Q2 delta hat Q0W is equal to Q2 if and only if W contains substring substring 0, 1. That's what we would like to prove, everybody. So let's see what we got over here. So we're going to be proving this using mathematical induction as per our discussion. So usually it's a good idea to lay out the game plan, what we're going to be doing. So proof. Proof. To prove the claim, we use mathematical induction on the length of the string W. Right? Good idea to make sure you say what you're going to do, right? Base step. Let's start with the base step. So this is when the length of the string is 0. So let's think about it. Then that means W is the empty string. So W is the empty string, and delta hat Q0 W is equal to Q0, right? That's what this would mean. So what does that mean, though? If it stays in Q0, and it is the empty string, right? Does it have any zeros in it? Yeah, it has no zeros, so it satisfies the first one. Now, please take note that Q1 and Q2, they both contain at least one zero. So in this sense, it is in fact satisfying the other two invariants, right? Because it's in Q0, which isn't Q1 nor Q2. So string epsilon contains no zeros as sought to be proven. So if you want to break this down a little further, it's saying that Q0 is satisfied, but all the other ones are rejected as expected. Now next, let's do the induction step. So again, we need to set up some things. It's about the setup. So fix some n greater or equal to 0. And let the length of the string that we are going to consider be n plus 1. Assuming, this is important, don't forget this, assuming the statement holds, holds for all strings of length n. That's their induction hypothesis. So we're assuming that this statement holds when the string is of length n. So what we're going to do is we're going to show from that we can extend one symbol. So as per we've seen before, we're going to now consider any string W equals XA where A is the last symbol of W. So now let's proceed. Now we got to show that the statement follows for when the length of the string is equal to n plus 1. So now we got to make sure we state this, because we're going to be trying to prove the statement follows from our induction hypothesis for all strings of length n plus 1. So we prove that the statement also follows for string W. So next, what do we got here? Well, X has length n, right? So we could use the induction hypothesis right away. As X has length n, by the induction hypothesis, we could say the following. So what can we say? Well, we just pull up our statement and we just plug her in for X. because it's length n. Well, it has length n, to be a bit more precise. So we know delta hat q0x is equal to q0 if and only if x contains no zeros, delta hat q0x is in, it gives us, so after processing string x, we're in q1, if and only if x ends with a 1. No, not a 1, right? I'm just making sure you're keeping track with what I'm doing. Ends with a 0, but does not contain substring, substring 0, 1, right? All I'm doing is just reiterating the invariants, but I can apply them on x because it's length n. So delta hat q0x is equal to q2 if and only if x contains substring 0, 1. Now, we have 3 possible states. Each one, we know exactly what x is going to have involving it. And a could be either 0 or 1. So we have 3 possibilities based on the invariants, but we have to append a. So for each one of these, we have 2 possibilities. So in total, there's going to be how many cases? 5 or 6, because one of them will end up being collapsing into one case. So technically it's 6 if I were to exhaust them in the most literal way possible, but most certainly you could write it down as 5 because one of them is just going to be the exact same one regardless. So, well, a can either be a 0 or a 1. We consider each possibility. So now all we got to do now is go through each possibility, and what we need to do for each one of them is make sure whatever the string ends up being for W in that case, it better be following the correct property, right? It has to follow one of these 3, but for string W. But it has to fall into the correct one. So, first case, delta hat q0 x is equal to q0, and a is equal to the 0. Miss Kitty, are you here for the cases? Yeah? Are you saying hi? But so we're going to have a case for when it's 0, when a is 0, and then we're going to have a case for when a is 1. We're going to do that for q2, and then q3 we'll see is not very surprising. Right, Miss Kitty? Yeah. Hello, Miss Kitty. So let's see what this one does. So string x contains no zeros, right? That's what we know. And 0 or more ones. Yes, Miss Kitty, yes. I didn't forget about the ones, okay? We got to remember about them. So we got 0 or more. That looks like I wrote more. 0 or more ones. So now we know that about x, right? It has 0 or more. It contains no zeros and 0 or more ones. And let's apply the extended transition function. It says that q0 w is equal to delta hat q0 x on symbol 0, right? But what is this? What is that? Yeah, Miss Kitty, yeah. What is it? Which state is it, Miss Kitty? Which state is it? Which state is going to be in upon reading x? Which one? Well, what does it say up there? It says it's going to be in which state, Miss Kitty? it's going to be in Q0, right? And upon reading a 0, where is it going to go? Where is it going? It goes to Q1. Well, what does that mean? It ends with a 0, and it doesn't contain the substring 0, 1, right? Which is exactly what you would expect to happen. So we'll say string, Miss Kitty, I made sure to remember, okay? String W ends with a 0, right? Because that's what it means to have A is equal to 0. String ends with a 0. String W ends with a 0, but does not contain substring 0, 1 as expected for the second invariant. I'll colloquially refer to, like, remember we have this for W, that's what we're trying to prove, right? So this is 1, 2, and 3. So this is number 2. So let's consider the next case, everybody. Okay. So, case 2. So case 2, this is when delta hat, remember now we have to consider when A is 1 this time. And A is equal to 1. Well, let's just see what happens. Well, delta hat Q0W is going to be equal to delta of delta hat Q0X given a 1, right? But remember, we know that this is Q0. We read a 1. What happens? Did we encounter a 0 yet? No, right? So we're still in Q0. It's still in Q0. And still contains no zeros as per the first invariant. As per the first invariant. So that's case 2. Next, now we're going to consider those that involve state Q1 and A is equal to 0. So in this case, remember that the string, if it's in Q1, X has to end with a 0. And right now, the last symbol in W is a 0. So that means that we're going to end up in which state again? We're going to end up back in, are we going anywhere forwards? No, right? We haven't read a 1. That's the interesting case I was alluding to some while back. So next, by definition, delta hat Q0W is equal to delta of delta hat Q0X, reading it 0. We already know this is Q1. Whoops, this is supposed to be, wait, no, yeah, this is X. In fact, I think this is all supposed to be X. For some reason I wrote X over there. No, wait, I got it correct there. Never mind. This here is okay. Miss Kitty, why didn't you tell me about that? She's just screaming at me. I'm sorry, Miss Kitty. Yeah, you're going to blame me on this one. Okay, fair enough. So, anyways, so now we know this is Q1, right? So, what's Q1 when I read a 0? Well, it stays in Q1, right? And it's still what? It still ends with a 0, right? And still ends with a 0. Yeah, exactly, Miss Kitty. It ends with a 0. And does not contain 0, 1, right? as per the second invariant. So far we're doing okay, right? We're about halfway through the cases. You can see that this is a quite verbose process, but well, certainly it's not like anything weird is happening. That's both a flaw but also a feature of this, is that we're exhaustively making sure that the invariants all hold appropriately. But it's a feature in the sense that we're checking to make sure each case is okay, but maybe as a flaw of this is that it's quite verbose. So this is why somebody might try to think of a very clever invariant that might work for a particular DFA as opposed to using just state invariants like this. However, this will most certainly work, and as long as you can apply it appropriately, you're all good. I mean, this isn't terribly challenging. It's just you have to be careful. And I mean, when you're dealing with this type of computer science work, you have to, like, especially when we're studying things of this kind, you have to be exact and careful. Even the very one way you phrase something could change ever so slightly the meaning of what you're trying to argue. So, as Miss Kitty helped me point out. So, anyways, we have the other possibility. So this is when A is 1 this time. So this one is interesting in the sense that we're actually going to go from one state to another state, and this is why I might use a state invariant. The cover cases like this one, especially. So then, delta hat Q0 W, upon reading W, well, what is that? That's delta of delta hat Q0 X upon reading a 1. And I know that is going to, this outputs Q1, right? But on Q1, if I see a 1, it gets me the Q2 because I've now detected a substring 0, 1, right? So string W contains 0, 1 as per the third invariant. Right? It's for cases like this that really state invariants are really helpful. And remember, this is when it happens when you detect the 0, 1, and this is at the end. So this happens at the end of the string. It means if you didn't encounter 0, 1 yet, this is the moment for which you encounter 0, 1. Now, final case. I'm just going to bound it all up into this one super case. So Q0X. Yes, Miss Kitty, I got it. We're not going to do two separate cases. Okay, Miss Kitty? Yeah, we're going to just do one. Why? Because I can just collapse it. Yes, Miss Kitty, I haven't forgotten about the one thing that we're going to try doing. And either A is equal to 0 or A is equal to 1, because it won't make any difference. If you remember our DFA, regardless of if you have a 0 or a 1, it stays in the same state. It stays in Q2. We just need to make sure that the invariant still holds. Like all of our invariants hold. Because remember, if it satisfies one of the invariants based on the way we organized our three invariants, our state invariants, all of them are unrelated. So if it satisfies one of them, it can't satisfy the other ones. Just please keep that in mind. Regardless, delta hat, so upon processing string W, it has to be, this is delta hat of Q0X upon reading A, which this is just delta of Q2A, which this is just Q2. And I'll make that a comma now. And and W still contains, yes, Miss Kitty, and still contains 0, 1. The third invariant still holds. This third invariant still holds. So now we've broken down every one of the cases. Now we just complete the induction step, and then we could just invoke the principle of mathematical induction, and we're done. Miss Kitty, are we going to finish the proof? Yes, yes. Okay. So the statement follows. The statement follows. Statement follows for when the length of the string is equal to n plus 1, finishing the induction step. Finishing the induction step. Now we just invoke the principle of mathematical induction to finish up the proof. Therefore, by the principle of mathematical induction, the statement is satisfied for all strings of That completes the proof. Now, we've proven the lemma. We're not quite done yet. We still have one thing that we still need to do, right? We proved that lemma. One part of that lemma tells us what we need to know, right? Well, let's put it all together now. So the only final state of M sub is Q3. So any string W accepted by M sub must follow delta hat Q0 W is equal to Q2. But what does that mean? If this is satisfied, that means if and only if what? W contains substring 0, 1, right? By our lemma. So if you could give it a name, it's usually a little bit helpful, like call it lemma 1 or something like that. By our lemma, any string W is accepted by M sub if and only if, it's very important, if and only if W contains 0, 1 as a substring. Proving the correctness. That S is looking a little little excited there of M sub. So now that we've had this all laid out, let's state this as a theorem now, because this is the argument. So as I said previously, if you want to just have a theorem proof kind of structure, you just use this argument as your proof. So theorem. So here's your theorem. So the language of M sub, I was going to say L sub. I'm thinking of submarine sandwiches, I swear, or something. I don't know. I'm just saying things now. So the language of M sub is a set of all binary strings such that W contains substring 0, 1. And we're done the example. Hence, we proved the correctness of DFA M sub. So indeed, this DFA, given any binary string, will detect if the substring 0, 1 is in W.